All right, these are notes for 5.1, the first section of chapter 5, and they deal with a randomization and the beginnings of our discussion of probability. And then we're going to um, look at some situations that we want to calculate the probability of a particular event happening, but we don't know how to do that, the calculation of the theoretical probability for that. So instead, what we're going to do is do some simulations using some chance devices, a roll of a die, a random digit table, that kind of thing, flip of a coin, that kind of thing. The whole chapter, chapter 5, is dealing with probabilities, but this first chapter is, the main topic in this first section of this chapter is simulations. And the College Board, year after year, when they after the AP statistics exam is taken and they release the results, nearly every year they say that one of the main topics that students struggle on the most is this probability simulations. And so that's what we're going to concentrate on this first section. All right, so you can see here that we're going to talk about probability as a long-term event, and then also we'll do some modeling of some simulations. All right, so this activity you might have already done in class. Some years I incorporate it in with the actual notes. Sometimes we do it as a precursor for the chapter. So if we've already done this in your class, then I would say fast forward through these notes, through these couple of next slides, and get to the rest of the notes for this section. All right, so we're dealing with a simulation here. And so the situation is that a special promotion for the new 20-ounce bottles of soda for a soft drink company. And they are trying to promote this by having a contest, and you twist the top of the cap off and you look under the cap, and it says one of two things. It either says you're a winner, or it says basically, please try again. In other words, you did not win. All right. The company says that 1 in 6 bottles is a winner. The prize is a free bottle of soda. Now, the store where you bought your bottle of soda is responsible for giving you your free bottle. And so it comes out of the store owner profits. All right, so 7 friends go into a convenience store and they each buy a 20-ounce bottle of soda. And when those 7 students take off the cap, they find that 3 of them are winners. 3 of the 7 are winners. And that's kind of surprising. And the owner is thinking like, oh, that seems like too many winners out of 7 bottles of soda. And so he's convinced that the company is lying and that the odds of winning are not 1 out of 6, but actually better than that. And so he's concerned because it's gonna cost him out of his profits. So what we want to do is simulate, well, how often would we expect that to happen, right? So if the probability of winning is 1 out of 6 and 6 friends went in to buy soda, we would expect on average about 1 out of the 6 to be a winner. So 7, yeah, maybe 1, maybe 2, somewhere between there you'd expect in the long run. So 3 is that really rare, right? And so that's what we want to simulate here. And so we're going to roll a die, and we're going to, it's convenient for us that a die, traditional dice, have 6 sides. And so we're going to designate one of those sides as winning and the other 5 as losers. And so we're going to just look at 6 as being the winner. So every time a 6 comes up, it's like buying a bottle of soda and twisting the lid off and seeing that you're a winner, okay? If any other numbers, 1, 2, 3, 4, and 5 show up, that means you did not win. So what you're going to do is you're going to roll a die. So, find a die somewhere and, from a board game or something, a traditional die that has numbers on it. and you're going to roll that die. And so I'm going to do that here. I roll the first die and I got a 4. All right, so I lost. And then the second simulation, right? I mean, the 7 rolls is really one simulation, but so I roll the die again, and this time I got a 2. And then I roll the die again, and this time I got a 6, so this one was a winner. I roll it again, I got a 5. I roll it for a 5th time, I got a 3. And then I get a 4, and then I get a 4 again. Okay, and so if we look, so in this case, if this simulates the 7 people going in to buy sodas, in this simulation, there was only 1 winner out of the 6. All right, and so what we would do if we were in the classroom is I would have you team up and do this again and again and again, and we would keep track of all the data. All right, so I've already done that. You can see here what the outcome is. So I did this simulation. I rolled the die 7 times, and I repeated 100 simulations. So I rolled the die 700 times, right? So 100 groups of 7 rolls, and each time I recorded how many 6s showed up. And then what I did is I created a dot plot of that. So you can see here to calculate, how likely is it that I would get something. Remember, we don't want to calculate just the probability that a 3 shows up. We want to calculate the probability that a 3 or more shows up, right? So our probability, we don't want to just do 3. We want to think of this dot plot is sort of a density curve. And so remember that density curves, you can't calculate probabilities of particular values, but a particular value or one more extreme. And so in this case, we really don't want to just talk about the 3 are winners, but what's the probability that 3 or more are winners? And so if we count up all those dots, you can see on the left there, I kept track of all of them, and there's 100 simulations. And of those 100 simulations, 17 had 3 6s or more, 3 or more 6s. And so that means that the probability that we would get a result as extreme or more extreme. Now we could have gotten 5, 6, or 7 that won, but in my 100, I didn't get a single occurrence of a 5 or a 6. It's possible I could even get a 7, but just not very likely, okay? And so we will, by the end of this chapter, know how to calculate the theoretical probability that this would happen, that we would get a 3 or more. But for now, we're going to rely on this simulation or the simulated probability. So according to our set of 100 simulations, we would expect about 17% of the time when 7 people play this game, we would expect 3 or more to win 17% of the time. Okay, so that's not very rare, and so yeah, the shop owner does not. And again, this is all based on the probability that 1 in 6 is a winner. So if 1 in 6 are actual winners, we would expect that we would get 3 or more wins out of 7 tries, 17% of the time. Not rare enough for us to really say, oh, the company's lying, right? So we would expect that outcome, or one more extreme, 17% of the time. Okay, so we want to look here at the idea of probability as being a long-term event, not a short-term event. So there's an applet that I'm going to open up here and show as well, that simulates flipping of a coin. And what this really is going to demonstrate is that in the short term, if I flip a coin, I might not get every other flip to be a heads or to be a tails. You can get runs of heads and runs of tails, but in the long run, you're going to get the outcome or proportions of your outcomes to be matching very closely to the theoretical probability. So if we flip a coin, we would expect heads to come up 50% of the time. Okay. Now in the short run, no, but in the long run, yes, we would expect the outcomes to match the theoretical probabilities. Okay, this is the applet that comes with, one of the applets that comes with our book. This one is allowing us to essentially flip a coin electronically. So what's interesting about this is I can change the probability that the heads comes up. So right now we'll leave it at 50%, but you can change that. Here up at the top. And then you can also adjust how many tosses you're going to do. So let's take it down to 1 and let's just toss it. Okay. So you can see that I tossed it and I got a heads. And, oh, sorry, let's try that again. Toss it once and I got a heads. Toss it twice and I got a head. So right now, actually, sorry, I got 2 tails. You can just make out the bottom of it where it's kind of, once I actually get ahead, you'll kind of see the graph, but it's going along the bottom because I've tossed it twice and I've gotten 2 heads. You can see that up here at the top, 0 out of 2. The tails is 2 out of 2. All right, let's toss it again. I've gotten 3 tails in a row, another tails, 4 in a row, 5 in a row. Okay, so there we go. Finally, we've gotten up, and you can see now it's graphing what the overall outcome is. So for right now, the probability of heads, or not the probability of heads, but the proportion of heads that have come up in my 6 tosses is 1 out of 6, so about 17%. You can see the graph here is up at about 7%. So if I keep doing that, you can notice we had 8 tosses, but we've only gotten 2 heads in those 8 tosses, and so that's fine. The short term, in the short term, we may not get exactly a 50% toss rate. The 50% of the tosses are probably not going to turn out to be heads in the short run. So we've set the probability of the heads being at 50. We know that's a fair coin. 50% of the time you'd expect it to be heads, but that's only in the long term. In the short term, we can find, like for example, we had the first 6 tosses, we had nothing but tails. So if we keep tossing, you can see I'm going to keep clicking the toss button, and you can see that in the long run, the proportion of heads is going to, and it's kind of gone over a little bit, but it will get closer and closer to the actual true probability of 50%. So probability is a long-term event. So when we say, oh, the probability of getting a heads is 50%, that means we would expect 50% of the tosses to turn out to be heads, but that's in the long term. We already saw the first 6 of the tosses were tails. So in the short term, no, but in the long term, yeah, we expect that to happen. I'm going to increase the proportion, the number of tosses to 200 and run it again and ask it to toss, and you can see it's still pretty far. Oh, now it's close. It's getting closer and closer, but now you can see, okay, now we're pretty close. The proportion of heads in the 283 tosses we've done so far is 0.488, so 48.8%. I'm going to do another 200. And you can see now it's approaching, it's getting even closer to that 50% mark. So 0.495. So 49.5% of the tosses were heads. So again, in the long run, short term, we saw it pretty far away, but in the long run, we would expect it to be pretty darn close. And we could just keep doing that, hitting another 200 and another 200. And you can see that the percentage is probably going to get closer and closer. Um, you know, yeah, it's about the same as what it was. But if we keep running this, we sat here all day long and ran it, we would see it. We could get it almost as close as we wanted. All right, so the probability, and just add a little detail here, probability of any outcome of chance behavior is always has to be a number between 0 and 1. So 0 would indicate that the outcome is not possible, and a 1 would mean that it has to happen all the time. There's no way it cannot happen. So it's certain. So the probability of something happening is 1. That would be certainty. Probability of it not happening would be the probability of 0. It's just never going to happen. Okay. So a couple of questions here. If a fair coin is tossed 5 times and the results are a head, a head, a head, a head, a head, so 5 heads come up in a row, then the probability that a tail comes up on the next toss is it 1? Is it greater than 1/2? Is it exactly 1/2? Is it less than 1/2? Or is it 0? All right, so the answer is C, it's still 1/2. So assuming, of course, that this is a fair coin and that the probability of a head coming up is 50%, that it's fair, just because we had 5 heads in a row, past behaviors do not affect future behaviors here. Each flip of the coin is independent of what happened in the past, and so your answer is still 50%. So if I take a coin and I flip it 6 times, a fair coin means the probability of heads and tails is equal, 50%. Which of these is more likely to occur? Will we get heads, tails, heads, tails, heads, tail? Or would heads, 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 heads be more likely? And actually, they're both equally likely. They're both very rare that we would get this, that any one particular path would be very unlikely. And we will eventually get to a point where we can calculate this, and the probability is pretty low. Let me see, it's 1 out of 64 chance that either one of those outcomes would occur. Because when you look at 6 heads and tails, there are 64 different outcomes possible. So any one outcome is 1 out of 64. So we'll get to those kinds of calculations more, but just know that these are both equally likely. All right, so what I would like to do with this is investigate your ability to generate random numbers. And so let's assume that I asked you for homework to take a coin and flip it 50 times and to record the outcome of those 50 tosses. And so now let's assume, like, okay, well, I didn't have time to do that for homework. So now 5 minutes before class, I'm just going to make up some numbers and I'm going to make them feel as random as possible. And so there are 10 little rectangles in front of you. So your goal in your notes is to write down 5 letters in each one of those 10 rectangles for a total of 50. So, write a heads, a tails, a heads, a tails, whatever you think, simulate without actually flipping a coin. Just mentally think in your head, like, okay, what would flipping a coin 50 times look like? So pause this video and take a minute. And so in each one of these rectangles, write down 5 letters for each, heads or tails is the results that you would predict. And so write down 5 in each one of those, and then that would be for a total of 50 heads and tails as you go across. So pause this video and do that. Okay, so now let's assume you've gotten those 50 heads and tails written down. What I'm going to do, rather than try to just simulate it, I'm actually going, I could flip a coin, but it'd just be faster if I looked at a random digit table. And I'm going to assume that every even number I come across will count as a head, and every odd number I'm going to count as a tail, just to make it quicker than actually sitting and flipping a coin. All right, so I'm going to look at row 101, and I'm going to take numbers um, one at a time, right? I'm going to use one digit to represent each one. If that digit is an even number, I'm going to call it a heads, and if it's an odd number, I'm going to call it a tails. So I'm going to transpose those numbers down into my boxes, and then I'm going to need some from the next row because there's only 40 in a row, and then I converted them. Again, if it was an odd number, it became a tails, and if it was an even number, it became a heads. And now what I want to do is count the runs. How many, count the lengths of the runs. And I want to do a tally of those. So for example, I'm going to look at my first run here. So I have 2 tails. And so if I look at my runs, that means I'm going to have 1 run of 2. I'm just going to make a tally. And then after that, I have 2 heads. And so that's another run of length 2. So I'm going to make another tally there. And then I'm going to look at the next letter is a T, and there's 3 of those in a row. So that means I have 3, a run of 3. And then I have a run of 1. I just have a single H, so that's a run of 1. And then I have a T, which is a single run. So I'm going to put another tally there. The next is an H, and I'm going to run that over to the next H. There's 2 H's, so that's a run of 2. And I'm just going to keep doing this. 3 tails, so there's a run of 3. And I think I got one more here. 3 H's, so that's another run of 3. So you get the idea. Just keep doing this. Go all the way across. Don't use mine. Use the ones you wrote down and do that same thing for yours. So again, pause this video. Come up with how many runs of length 1, of length 2, of length 3 that you have. And pause this video while you're doing that, and then we'll come back. We'll come back and talk about the results. All right, so my run is actually a randomly generated. So I mean, I did not flip a coin, but I did use a random number generator, the random digit table. Whereas the numbers you came up with are just was more of a thought process, right? You weren't actually randomly creating those. And so you might want to, it's just interesting to look at. You might look at the number of runs of length 1 you had. So I had 7 runs of 1. Typically, students tend to have a lot more than that, right? They have a lot more than 7. They end up having a lot more, but then a lot less on the high end. So because people don't tend to think that there's going to be a lot of runs of size 4 and 5, if I ask the whole class now, like, oh, well, how many people had runs of 5 or more? Probably not very many would have that. And how many runs of 1 you had? Most people have in the teens or double digits. So my whole point of this is randomization looks a lot less random than it is sometimes in what people kind of think is going to happen. So you think it's going to flip-flop, heads, tails, heads, tails, heads, tails, a lot more than it actually does. And you end up getting runs longer than one, much more often than you actually would anticipate. Okay, so again, the behavior is a long-term event, so the probability of 50%. Yeah, it's a long term. Half of them will show up heads, half of them will show up tails in the long run, but in the short run, you end up having runs that are much longer. All right, some myths about randomness. All right, so the short run regularities. The idea of probability is that randomness is predictable in the long run. So on the short run, you can't really make predictions. And this is why gambling and like casinos with roulette wheels and things, yes, I know I can have predictable behavior in the long run. In the short run, I could win, right? I would beat the house in the short run. But if I sit at the table betting long enough, the house will win ultimately because it understands this long run. In the long run, the rules of probability will apply. And so they will make up their money in the long run. But in the short run, people gamble because in the short run, they can win. But in the long run, they won't ultimately. All right, so you can't confuse short run versus long run. Probability is a long run event. All right, and then this law of averages, another myth. Probability tells us that behavior evens out in the long run. So future outcomes are not affected by past behavior. So, sometimes you hear about people who keep track of all the lottery numbers that show up. And they might say, oh, a 2 hasn't come up in a long time, so that's bound to come up, more likely to come up in the next lottery than other numbers. And that's not false. Past behavior does not affect future behavior with independent events like that. Okay, so we're going to use a 4-step process when we are doing these simulations. So if we do a simulation, we first want to sort of answer the, ask in the state, we want to say what it is we're trying to answer. What is the question we're trying to estimate? What's the probability we're trying to estimate? All right, how likely something is to happen. And then we're going to say, okay, what kind of chance device are we going to use? Are we going to roll a die? Are we going to use a random digit table? Most often, we're going to use a random digit table. I won't have everyone rolling a die in the middle of a quiz or a test, so we'll be using a random digit table more often than not. So we're going to say how we're going to use the random digit table, how many digits we're going to look at, what kind of digits are we going to ignore, what do the different digits mean, that kind of thing. So say how we're going to use our random digit table, and what are we going to record sort of at the end. And then we'll actually do the simulation, and more is better, but sometimes we'll do 20 or 30. In the real world, we'll do 100 or 1,000, but for the process of doing it for a problem, we'll probably limit it to 10, 20, 30 simulations. And then based on how many outcomes we got in our simulations, we'll answer what the simulated probability would be. Okay. So the physical things that we'll be using are the random digit table. You could use some sort of spinner or die. You could also use technology to generate random numbers. All right, so here we're going to do an example of a simulation, and we will use our 4-step process so to demonstrate how you'll do this, because you'll have a homework problem that's asking you to do a similar thing. All right, so at Montclair High School, assume that there are 95 seniors who have passes to park on the street. A monthly lottery is held, and 2 lucky winning seniors get to park next to the principal for that month. All right, Mr. Rogers is in charge of parking at Montclair High School, and as a result is the person who randomly chooses the 2 winning seniors every month. This month, the 2 winners are from Mr. Rogers' AP Statistics classes. Students in Mr. Feinstein's AP Comp Sci class suspect that Mr. Rogers has fixed the lottery and may even be selling the monthly parking passes to help pay for his planned summer vacation in Europe. Of the 95 seniors who are eligible for this lottery, 28 of them are in Mr. Rogers' AP statistics class. Okay, so what we want to do is try to decide whether or not how likely, what's the probability that Mr. Rogers could randomly pick 2 students out of the 95 and get 2 that are his own students. So what's that probability of this happening? Okay, and again, we'll learn how to calculate theoretical probabilities later in the chapter, but for now we're going to do a simulation. And again, we're going to use our 4-step process. All right, so is it plausible that Mr. Rogers carried this out fairly? That's really what we want to ask. We really want to know what's the probability of this happening. If the probability of this happening is very low, then it probably didn't happen by chance and Mr. Rogers cheated. But if the probability of this happening is high, then we probably would say, he might have cheated, but it's possible that it could have happened. So we can't, we can't punish him. Okay. So we're going to use, again, these 4-step process. So the state, we want to say, okay, what is it that we're trying to calculate? We're trying to calculate the probability that 2 of his students would have been picked for this lottery, right? So what's the probability of that happening? So something like, what's the probability that 2 of Mr. Rogers' AP students would have been randomly chosen out of the 95, right? So there's 28 of his students. So what's the likelihood that 2 of his 28 would be chosen out of the 95 total students? All right, so how are we going to do this? This is where the plan comes in. So we're going to use a random digit table. And how are we going to use the random digit table? That's the key here. All right, so we're going to look at 2 digits at a time because there are 95 students total. We want to set up some of the numbers to represent Mr. Rogers' students and some of the numbers to represent non-Rogers students, right? So we'll count 0, 1, remember 2 digits at a time, so 0, 1 through 28 will represent Mr. Rogers' AP statistics students. And then the 29 through 95 will represent non-Mr. Rogers students, so other seniors who are not in Mr. Rogers' class. All right, so numbers that are beyond number 95, so 96 through 99 and 00 will be ignored. Now we have to think about repeats too. In one particular trial will be represented by picking 2 numbers, right? And so that same student could not be picked twice. So within the one trial, we'll ignore repeats. But from trial to trial, no, we will, everyone's name is thrown back in the hat. Someone could win 2 months in a row. So from trial to trial, month to month, yes, we can have repeats. But within the same month, the same student can't win both passes because you can only park 1 car. Okay. All right, so each trial is going to involve a pair of valid 2-digit numbers. And then we're going to repeat this many, 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 many times. And what we want to do is we want to count the number of trials, the number of 2-digit numbers that had both numbers in the range of 0, 1 to 28. So that means both numbers, both students would be Mr. Rogers' AP statistics students. All right, so we want to do the do. So we just pick a number. Now I'm starting on row 106, and I'm going to use 2 digits at a time. So we might look here and say, okay, so we have 68 is the first digit, and that's a non-Rogers student. And then we have 41, that's also a non-Rogers student. So in the repetition 1 or trial 1, we have 2 non-Rogers students. Okay, so then the next one, we have a 73 and a 50. So we have 2 numbers that are, again, non-Rogers students. So 2 non-Rogers. Then the next one is a 13. Okay, that's a Rogers, and a 15. All right, that's a Rogers. So in our third one here, we get a success, right? So right now, if we stop now, which we would not want to do, but 1/3 of the trials seem to be situations in which both students are from Mr. Rogers. Now we'll do, of course, a lot more than that. And so let me look and see, let's see what the next one is. So, okay, so I went ahead and ran them all here. So you can see here, it's a little tedious, but I ran 36 simulations or 30 different trials, 30 trials. And so you can see I kind of highlighted the ones that have 2. So the third one has 2 Rogers students. It looks like the 21st one had 2, the 22nd one had 2, and then the 26th one has 2. So we ran 30 trials, right? We ran 30 trials here, and we had 4 successes, right? So we want to think about what's that probability. We really want to think of it as not, we don't want to say things like the probability of this happening is, because this isn't a theoretical probability. We want to definitely say that we would expect the probability to be about what we got, or we want to say that the simulated probability. And so we want to look at here. So in our 30 simulations, this is what the conclusion should look like. 30 simulations, 4 of the simulations had outcome that included 2 of Mr. Rogers' AP students. And so this is roughly 13% of the time we would expect this to happen. So that's not really that rare, right? And again, we'll typically use the threshold of 5%. If it happened less often than 5% of the time, then that's kind of rare, and we would call into question whether Mr. Rogers is conducting this fairly. But it happening just by chance 13% of the time, then, you know, that's not so rare. So it's not so rare that, or so unlikely that we can say that Mr. Rogers is cheating or that he rigged these lotteries. All right, so your homework for this section is 1, 3, 7, 13, 15, and 23. Number 25 is number 25 is a 4-step process, and I'm telling you here, and write this down somewhere because I don't know that I wrote this anywhere on your page, but on 25 it probably does not say what row to start on, and so if we all start on row 116, we'll all have the same answers if we do our simulations right. So number 25 is dealing with a simulation. Start on row 116 when you get to your random digit table, and then also do 10 trials. And if you do 10 trials and you start on row 16 and you do it properly, we should all then get the same simulated probability, and we'll be able to tell whether you when we go over homework, can tell whether you did it correctly or not.